In this video, I will explain the hint. I will explain the application of virtual energy method. Actually, we use virtual energy method or virtual energy principle to find the deflections or displacement or rotations because of applied loads. As applied loads, I mean single loads or distributed loads or single moments. Distributed moments are generally not applied on our structures. First of all, I will show three examples to explain how energy equations are written. I will do this step by step. Now, first, consider our first example, as you see here on the left, on the first page. Now, we see here our structure is consists of one spring, and it's located vertically. Its self-weight is neglected, and here it's fixed. This is a fixed support, symbol of fixed support. Now, initially, time 1 is the initial time. Time here I mean 1 hour, 2 hours, 3 hours, but not the passing periods like 30 minutes, 15 minutes. The time moment. So time 1 is a time moment, the initial time. And we, since it's structural mechanics and analysis, all loads are static loads. Means that they are applied gradually, slowly. So the average load value is 1/2 of the final load value. This means that initially P is 0 and finally P has the value of just P. Okay? But the average value of P is, which is increased from 0 to its final value, P is 1/2 times P, 1/2 P. Okay? So when we are writing our energy equations, we use the average value of the static load. Actually, time is not neglected in static, but loads are applied very slowly so that velocity is 0. The movement velocity, the compressing velocity of the spring is almost 0, and the increasing amount of the load is very low, so that it's almost 0. Not 0, but almost 0. I think that for 10 Newton, it's 0.1 or 0.0001 Newton, almost 0. Okay, that's an assumption. So time is not neglected, time is very long, but the velocity and acceleration are 0. So when we are writing our energy equation, you know, energy equation is conservation of energy. We know kinetic energy and potential energy at one time equals to kinetic energy plus potential energy or another time. We can select any time. But here in this example, we select the initial time and the final time. So time 1 is the initial time and time 2 is the final time. So T1 is the kinetic energy at time 1 and T2 is the kinetic energy at time 2. V1 is the potential energy at time 1 and V2 is the potential energy at time 2. I might have done some grammar mistakes here. I'm speaking English as a foreign language. I apologize because of that. But mathematics has no language. Please try to understand what I am trying to explain here. Ignore the other punctuation or some other grammatical mistakes and errors. So potential energy is divided into two. From this dynamics, mechanics or materials 2 lecture, you know, in dynamics, the potential energy is divided into two. It has two parts. One part is because of external forces, and the other part is because of the internal forces, or the energy stored in the structure. Here the structure is the spring. So V1 is composed of V1F and V1E. V1F is potential energy of external forces because of external forces at time 1. And V1E is internal forces at time 1. Similarly, V2F is potential energy of external forces at time 2, and V2E is potential energy of internal forces at time 2. According to dynamics, T1 plus kinetic energy and potential energy, the summation of both energies at time 1 equals to summation of energies at time 2. Because of depending upon the conservation of energy rule. There is no conservative load here, friction load or something like that. Since all loads are applied gradually, slowly applied, that I explained in the beginning, in statics, velocity and hence kinetic energy is zero. As a result, potential energy at time 1 equals potential energy at time 2. Now, potential energy, how we write the potential energy? Remember from the gravitational potential energy, mass times gravitational acceleration, it's m times g is a force, times mg h. H is the distance between the load and a reference point. So potential energy, to be able to write a potential energy, we need a reference line. So the reference line is selected here as the final totally compressed position of the spring is selected. And we have to, in the mgh, h must be the difference which is in line with the line of force. So in the direction of the force, or in the sense of the force, we have x here. Our force is vertical, and x is vertical distance. So at point 1, our average load is P over 2, and its distance to our reference line, aligned with the forces line, is x. So load times x, like mg is the load, times h, mgh, 1 over 2p times x is V1F, potential energy or external forces at time 1, according to reference line, selected reference line. We select the reference line. We decide from which point or from where our reference line passes. And initially at time 1, our spring is not compressed or not elongated. As a result, there is no potential energy is reserved or accumulated in our spring. So V1E is 0. Okay, this term is 0, as you see here. So this is P over 2 times the distance from the point of load to the reference line. Okay, like mgh. And similarly, V2F is the potential energy of the force at time 2, according to the reference line. At time 2, P is here, and its tip is on the reference line. So there is no distance. Distance is 0. As a result, V to F is 0. And the elastic energy or the internal forces accumulated in the spring is, as you all know from the dynamics or statics, 1 over 2 times K times X squared. So consequently from this equation, as you all know from dynamics, P is known, the spring constant is known, we can calculate the displacement. This is our first example. In this example, we learn how to write this energy equation using a very simple example. Now, let's come here. This is actually very similar example, the second example. But as a civil engineer in civil engineering applications, we are not interested in springs. We are interested in beams, columns, or similar structures. So maybe the potential energy of forces are written similarly as given in the first example, but the elastic energy stored in a beam, in a structural component like a column, is calculated differently, but very similar. So the same equation applies here. We know since the velocity is 0 when static loads are applied, or when loads are applied statically or gradually or slowly, T1 and T2 is 0. We select, this is the time 1. This is P is increased from 0 to P. So the average value of our external single concentrated load is 1/2 P, 1/2 times P. Okay, and the displacement in the line in the sense of force vector is in the magnitude of x, as you see here. Okay, this displacement has not been done in time 1. Load is applied here, no deflection is done, so no elastic energy is stored in the beam. The beam hasn't made any deflection or any deformation. So the at time 1, the elastic stored energy is 0, and reference line is again selected as the deflected shape of beam is selected as the reference line, because the deflected shape of the beam is the curve in which our structured beam is in equilibrium, has reached its equilibrium position. Actually, I didn't need to select the equilibrium position. I can select reference line and a line when I'm writing this. It's important to notice this also here. Anyway, reference line is selected as this line. I select the reference line, this line. Okay, I can select arbitrarily any line. According to this line, I have to write this line here. It's not there is no deflection at time 1, but I use this dashed line, which is equal to the real deflected shape of beam, which is in equilibrium at time 2. Here I drew it here to be able to see the displacement amount in the direction of P. It's x. So like similar to MGH, potential energy because of external load is its average value, load's average value, because it's statically applied, 1 half p times the distance from the tip of the load vector, force vector, to the reference line vertically, and it's x. So 1 half p times x is elastic, potential energy or external force. So this part is equal to 1 half p times x again. Now this time I know the elastic energy is written, from strength of materials and structural mechanics and analysis. 1 half times, this is the moment function, which is calculated under load P, or the beam. It's m square divided by EI. Here E is the elasticity modulus and I is the moment of inertia, as you know. So if we eliminate the 1 half or 0.5 numbers here, we can calculate the deflection or the displacement x in terms of known values of P, and m is also known because m is calculated from structural mechanics and analysis for determinate or indeterminate structures. Now I am speaking here and giving examples from determinate structures to make the topic easy. So the solution is obtained by means of writing energy equations, as we know from the dynamics. Now in the third example, I have selected 3 concentrated loads. They are applied statically, gradually, or slowly. That's why I put their half average values here. Average value of P1, P2, and P3 are here. In the beginning, loads are applied, located on the beam, no deflection. In the end, loads are on the deflected shape, which is also in the equilibrium under the applied loads. Okay, and I draw the selected reference line, which is the equilibrium line of the beam here, using a dash line. Okay, so according to the by myself selected reference line, the potential energy of external forces at time 1 is this. But when I am writing the internally stored energy of the beam, or internal or energy of the internal forces of beam, potential energy of the internal forces of the beam, you see at time 1 the beam is straight, as here the spring is not elongated nor compressed. So the stored elastic energy in the beam at time 1 is 0. So again here those two terms are 0. The kinetic energy is also 0. At time 2, the final position, according to our selected reference line, load P1 over 2 times the distance between the tip of the load, tip of the arrow, and the reference line is 0, because the load itself is on the reference line. So P1 over 2 times 0 is 0. Okay. Similarly, P2 over 2 times 0 is 0. P3 over 2 times 0 is 0. So as a result, V2F potential energy of external forces at time 2 is 0. But our beam is, as you see here, the beam is bent, and the elastic energy stored in it is calculated by means of this equation. Okay, but here m is the function, moment function, calculated using P1, P2, and P3 value. When we are calculating m function, we use P1, P2, and P3, not 1/2 of P1, 1/2 of P2 and 1 of O P3. When we calculate reaction forces, internal forces, moment, shear force, we use not the half values or the average values of external loads. We use the final load values of the static loads. That when we are writing energy equations, we have to use the average value of the loads because time is not neglected in dynamics, and energy equation is written when time does exist. Here there is time 1 and time 2, and the value of P1 changes from 0 to P1. So the average, we have to use the average value. So when we replace these values into, substitute these values into our equation, you know, one of values are eliminate, one of values eliminates each other, and we got this value. We know P1, P2, and P3. We can calculate from static strength of materials, and we know elasticity modulus of the beam material, and from the beam section we can calculate moment of inertia. So this value is also known. But we have just one equation, but we have three unknowns: x1, x2, and x3. So I cannot calculate the value of x1, x2, or x3 using this energy equation. In the third example, I illustrated how energy equation is applied. Now let's turn the page. Let's make the screen composer one page. For one page. Sorry. I can't see how much time it means. Let me a bit breathe now. I'm tired. 20-30 seconds. I will complete. Okay, let's continue. Now, one man in the past understand if there is more than one external value, I cannot calculate the displacement, and I can even if there is just one load, one concentrate load, I can calculate only the displacement under the load, not the displacement at any point on the structure. Then one theoretician in the past, virtual energy method. There is virtual displacement and arbitrary displacement, but this person thought that actually this is how virtual energy method is used in structural analysis by means of unit loading. It's not an arbitrary loading. The guy in the past, the theoretician, understands I have to use some specific loading to calculate the displacement under the loading or anywhere on the structure because of the loading. And he invented a loading. This is the unit loading. The mentioned virtual energy method used or employed in structural analysis is actually application of energy methods by means of additional unit loading. This is the development of the method. So the guy, as you know, there are x1, x2, and x3 here. To calculate x1, for example, x1, let me place 1 unit load at the place of x1, and it's in direction, in x1 displacement direction. But it's again a static loading applied gradually. So consider its average value. This is time 1. He took the same structure, removed all P1, P2, P3 loads, and applied 1 unit loading in the direction of x1, which is the value which want to be calculated using hand calculation. And as a result, time 1 is when 1 unit load is applied. Actually, at time 1, its value is 0, but between time 1 and equilibrium position time 2, its average value is 1/2 times 1. And the deflection of the beam under unit load 1, which is also in the direction of x1, is delta here. And the reference line is taken as this shape, okay, which is the equilibrium shape of the beam under 1 unit load. Okay, but I write here always 1/2 times 1 because it's the average value of 1 unit load. According to the reference line, to this reference line, the potential energy of external loads, which is V1F, is load times the displacement in the direction of load. So 1/2 times delta, or delta divided by 2. Okay. And since the beam is not deflected or deformed at time 1, the internal stored potential energy is 0. At time 2, I do so. Now unit load comes here, and the load tip is on the reference line. Okay, and I applied new static loads P1, P2, and P3. These P1, P2, and P3 are the loads in our previous example. And then I write the potential energy of the external forces. But all external forces, the new loads and the previous loads, are all on the reference line. So their distance to the reference line are all 0. So potential energy of external forces at time 2 is 0, because force times the distance is 0, because distance is 0. And the internally stored energy is because of this 1 unit load between time 1 and time 2 is, as you know, from statics, this value. Now, since the external load is the 1 unit load, I put here 1 here, and 1 square means that. Okay, that's so. Now, at time 3, because of the new added loads, our beam reached a new equilibrium position. But when I am writing, this is the hint here. I write here the average value of 1 unit load, here the average value of 1 unit load, because it's increased from 0 to 1. But between time 2 and time 3, the value of 1 unit load has never changed. It's kept constant. So here the values 1 plus P1 over 2, because actually P1's value was 0 here at time 2, and its value is P1 at time 3, so its average value is P1 2. It's a bit confusing here, but if you repeat this video again and again, and if you download this document, you will understand it. Similarly, the values here are here, but okay, and this is our deflected shape. Now let's write the potential energy of external forces, but again, according to our reference line. Reference line never changes. When I write the potential energy of external forces at time 1, reference line is same. At time 2, reference line is same. At time 3, reference line is same. So again, according to the same reference line, I write the potential energy of external forces here. Now the external forces is that one. 1 plus P1 over 2. And its distance to my reference line is x1. Okay. But their directions are reversed. Okay? Reversed. It's like in MGH. If you select the reference line below the MG load, your potential is positive. If the reference line above the MG or the dead load, your potential energy is negative. This is taught in statics and dynamics. Please refer to the books of dynamics. So its potential energy of force is negative because the reference line is above the forces. So they are all negative. Okay. If I rewrite it, I will obtain this equation. Now, when I am writing the stored elastic energy at time 3, I consider only the deflected shape, not the reference line. Now, when the beam came to that equilibrium condition, first of all, because of one unit statically applied load, its average value is so this parts, because of this part, only this part, we have the internal stored energy of that one. Okay? Which is same as that. But here I have one unit load, but the deflection corresponding and because of this one unit load, it's constant. It's constant. So M1 is the internal moment, and the corresponding curvature is, as we know from the previous example, the moment function because of P1, P2, and P3. This is the internal energy because of one unit load. But its value is constant from that time to that time, or from time 2 to time 3. Okay, so from this reference line to this last reached equilibrium line, one unit load is constant. So there is no 1 over 2 here, no average is considered. But because of P1, P2, and P3 is increased from zero values from the reference line to the last equilibrium line, its internal energy includes 1 over 2 here. Okay. So let's write the same equation depending upon the conservation of energy. As we know from the dynamics, kinetic energies are 0, and from here we learned that V2F is 0. And now check that I can write this equation between time 1 and time 2, between time 1 and time 3, or between time 2 and time 3. I prefer here writing this energy, conservation of energy equation between time 2 and time 3. And I replace the equations I explained above. Here I substitute the values of these symbols, energies here, and these two values eliminate each other correspondingly, mutually, since they are equal to each other, and I have this value. From the third example, we know that this value equals to that value. And if I replace, instead of this value, I have this equation. And since here there is minus and here there is positive, but their absolute values are equal, these two values are also removed from our equation. And finally, I have obtained the value of x1 displacement. So m1 is obtained under 1 unit loading, but it's, as you know from the statistics, when I am calculating deriving the function of m1, I use not the average value, but the final value of 1 unit load, that is the 1. And when I calculate the moment function m, as you know from the statistics, I use the final values of P1, P2, and P3, not their average values. Application, I applied on the beam P1, P2, and P3, not their average values, obtain a moment function, and then to calculate x1, I replace here 1 unit load in the direction of P1, and I calculate m1 moment function developed because of 1 unit load. And then I calculate x1 using this formula. x2, x3, or any displacement or any rotation is calculated in the similar way. Here, the development or the invention is one guy invented this. Invented this unit loading and writing this 3 times. He invented these 3 phases and writing this equation between second and third time, and then calculated this value. And then briefly, without this explanation, he wrote, presented in the structural mechanics and analysis books, use 1 unit load, obtain moment functions, and calculate the displacement. Okay. But its theory and the physical understanding comes from here. But to reach that point, I used 3 examples so that the learner obtains some basic at the foundation to reach that point. Okay. Please repeat this video sometimes, and you will understand how this method is developed or invented by someone using conservation of energy and these 3 time moments. So let's finish the video. Thank you very much, all of you. Please don't forget to subscribe to my